Hi everyone. Today we will discuss about the NMR spectral table and how easily we can remember this NMR spectral table. Let us take one structure like this. This is a propane, and in the propane how many NMR peaks are observed if we are going to consider the proton NMR spectroscopy. So here we have to identify the different types of protons and their environment. So let us expand this structure, and when we expand this structure we can observe different types of protons like this which are attached to the carbon, and these are the methyl protons. And at the other terminal again we can observe the methyl protons. All these 6 methyl protons are equivalent, so they will give one NMR signal. So let us indicate these protons by letter A. And now we can see the nth type of protons here. These two protons are methylene protons, which can be indicated by letter B. Now if we see the position of the peaks corresponding to methyl and methylene protons in the propane, we can have an approximate chemical shift values. For example, here the methyl proton can have an approximate chemical shift of 0.9 ppm, whereas methylene proton can be observed at the 1.3 ppm. So in this way, in the NMR spectra, peaks corresponding to the different types of protons can be identified by their approximate chemical shift values. Now let us take another example. Here we have taken the acetaldehyde, and again let us expand the structure. So here the hydrogens which are attached to this carbon, all these are the methyl protons, so they will give one type of peak. Similarly, the hydrogen which is attached to this carbonyl group will give another type of peak. So totally the acetaldehyde can give the two types of peaks. Now if we see the chemical shift values of these two types of protons, methyl protons will show a peak at 2.2 ppm approximately, whereas the protons in the aldehyde functional group will show a peak at the 9.8 ppm. In the previous example, we have seen that the methyl protons in the propane has shown a chemical shift at 0.9 ppm, but here in the acetaldehyde they have shown a peak at the 2.2 ppm. So what happened here? The chemical shift is going to be increased. Why this chemical shift is going to be increased? You can see here that the methyl group is attached with the aldehyde, and this aldehyde is having a carbonyl functional group. This carbonyl functional group acts as an electron withdrawing group, and because of this effect the methyl protons are going to be deshielded, thereby their chemical shift is going to be increased. So whenever the protons are deshielded because of any electron withdrawing groups present adjacently, the chemical shift will be increased. Similarly, let us take another example here, the ethyl bromide. Now again, if we expand the structure, here you can observe that it is having the methyl protons which can be indicated by letter A, and it can also have the methylene protons which can be indicated by letter B. And if we see the chemical shift values, the methyl proton is having 1.7 ppm and methylene protons are having 3.5 ppm approximately. Now if we compare again with the propane, the 0.9 ppm is corresponding to the methyl protons in the propane, but here the methyl protons have shifted to the 1.7 ppm. Similarly, the methylene protons, they are shifted from 1.3 to the 3.5 in the ethyl bromide. So again here this is because of the presence of bromine. So bromine is again electron withdrawing group, so it can produce a deshielding effect on both methyl as well as methylene protons. It will have more effect on the methylene protons because it is directly attached to the methylene protons. So we can observe a high shift from 1.3 to the 3.5 ppm in the methylene protons. So here because of presence of bromine, the deshielding effect is observed, but bromine is not having any pi bond, but it is having n electrons, and because of its high electronegativity can produce a high deshielding effect on both methyl as well as methylene protons. So if we observe a chemical shift value of a particular proton in the NMR spectra, we can expect what is the chemical environment of that proton. If a methyl proton is having 0.9 ppm, that means it is isolated, it is not attached with any electron withdrawing group. But it is shifted to the higher values, then we can say that it is going to be attached with an electron withdrawing group. By this we can assess the chemical environment of the protons in the NMR spectra. In order to do this, we should know the approximate values of the different types of protons in the NMR spectra, so that we can say that whether the chemical shift is either increased or decreased. So now in this video, let us see the approximate values of the different types of protons. and how easily we can remember this table by splitting these chemical shift values into the 6 types of groups. So now let us go with this NMR spectral table. So we will see the type of electron and what is the chemical shift range approximately. For example, if protons are present in an environment where there is no pi electrons, so the chemical shift range will be 0 to 1.5. And if the protons are having an alpha pi electron, that means adjacently a pi electron is present, then they will have a chemical shift of 1.5 to 2.5. And if they are having an adjacent n electrons, lone pair of electrons, they will have a chemical shift of 2.5 to 4.5. And here you can see that whenever lone pair of electrons are adjacently present, the chemical shift range is more. But it is not because of the n electrons, it is because of the electronegativity of the elements which are having the n electrons. Similarly, if the protons are present directly attached with pi electrons, they will have 4.5 to 6.5. And if they are attached with the aromatic pi electrons, 6.5 to 8. And so if they are having both pi as well as n electrons adjacently, then they will have 9 to 12 as the chemical shift range. So now let us see the different types of examples for this spectral table. So let us start with the protons which are not having any pi electrons. Simple one is the alkyl protons. In the alkyl protons, you can see that these protons are attached with the carbon which is not attached with any pi bond or n electrons. So these are going to fall in the chemical range of 0 to 1.5. So for example, we can take the methyl protons. These methyl protons approximately fall at the range of 0.9 ppm. And similarly, methylene protons are going to fall at the 1.3 ppm, and methine protons are at the 1.4 ppm. This is approximate chemical shift, but these chemical shift values will change based on the structure and other functional groups present. Second one is the alpha pi electrons. So this is one of example of alpha pi electrons, and this is another example. You can see that here the protons are attached with a carbonyl group which is having the pi electrons. Similarly, here again the protons are attached with a carbon which is again having the pi electron. So if any alpha pi electron is there, then they can have a chemical shift range of 1.5 to 2.5. So let us take one example here. This is the propanol. In the propanol, you can see that these protons are adjacent to this aldehyde. So they will fall in a range of 1.5 to 2.5. So in the propanol, we can see an approximate value of 2.4 ppm of this methylene protons. Similarly, if you take the propene, here again these methyl protons are going to fall in a range of 2.0. So these protons are going to fall within 1.5 to 2.5 when they are having a adjacent pi electrons. So this we can remember as the protons attached with a alpha keto as well as allylic protons. So allylic protons as well as alpha keto protons will fall in a range of 1.5 to 2.5. And third one is the alpha n electrons. So let us take one example here. Here you can see the protons which are attached to the carbon having a heteroatom, and this heteroatom is having the n electrons. So such type of protons are going to fall in the range of 2.5 to 4.5. So this heteroatom may be either oxygen, nitrogen or halogens, whatever may be. All these are electron withdrawing groups which will increase the chemical shift by their de-shielding effect. For example, we can take the alcohol. In the alcohol, the protons adjacent to this OH group will fall in a chemical range of 3.5. That means it is in the range of 2.5 to the 4.5. Similarly, we can observe the other types of protons like in the amines as well as in the alkyl halides. In all these, the protons which are present to the alpha to the heteroatom are falling within 2.5 to 4.5. So we can simply remember this range as alpha hetero. If alpha hetero will fall in 2.5 to 4.5. And fourth one is the pi electrons. So let us take one example here. Now you can see that these protons are directly attached to the carbon which is having the pi electrons. So such type of protons will fall in the range of 4.5 to 6.5. So these type of protons can be remembered as vinylic protons. So these vinylic protons will have a high chemical shift compared with the allylic protons, because here the proton is directly connected with the pi electrons where it will have more de-shielding effect compared with the allylic protons. So vinylic protons will fall in the range of 4.5 to 6.5. Fifth one is the aromatic protons. So aromatic protons will fall in the range of 6.5 to 8.0 because aromatic ring system produce more de-shielding effect, so they will have more chemical shift. Let us take one example of toluene. In the toluene, you can observe two types of protons. This is one type of proton which is attached to the aromatic ring system, and this is another type of proton which is attached with the aliphatic ring system. Now this aromatic proton is having a high chemical shift around 7.0. You can see that it is in between 6.5 to 8.0, but here this allylic proton is going to have a chemical shift of 2.3. You can see a large difference in the chemical shift of aromatic protons because of high de-shielding effect. And aromatic ring system produce a magnetic anisotropy which produce a high de-shielding effect. Sixth one, both alpha pi as well as n electrons. So let us take one example of aldehyde. So in the aldehyde, you can observe the protons are there which are adjacent to this pi electrons as well as the n electrons. Similarly, in the carboxylic acid, this proton is attached with the oxygen which is having the n electrons, as well as it's also having the adjacent pi electrons. So in such case, the chemical shift value will be 9 to 12. So here the protons are in an environment where they are attached with the adjacent pi electrons as well as they are attached with the n electrons. So when both of these are present, they will have a high de-shielding effect, thereby they will show high chemical shift. So they are going to fall in the last of the NMR spectral table, that is 9 to 12. So these protons we can remember like aldehydic protons as well as acidic protons. So these are going to fall from 9 to 12. So in this way, we can divide this NMR spectral table, which is actually having the chemical shift values from 0 to 12 into 6 divisions, and we can easily remember these divisions based on the environment of the proton. For example, proton having no pi electrons, or proton having alpha pi electrons, proton having alpha n electrons, and protons directly attached with the pi electrons, then aromatic pi electrons, then both pi as well as n electrons. So in this way, we can easily remember this approximate chemical shift values of the different types of protons in the NMR spectral table. So that's for today. If you like this video, please subscribe to our channel and share this video with your friends and post your comments in the comment box. Thank you for watching this video.